Hi, I Aziz welcome you to CoedMaster, and in this video I am going to talk about recursion tree method. In previous video we have seen that how to write a recurrence relation of a recursive function, and in this video we are going to see how to solve recurrence relation using recursion tree method. So let's get started. So this is the same example we have used in our previous video. The recurrence relation of this recursive function is Tn is equal to Tn-1 plus c. So with the help of this recurrence relation, let's try to construct recurrence tree first. So how we construct a recurrence tree? Let me show you. So what we do in recurrence tree, we write a function n first, because when we run this program, we are obviously going to call this recurrence function, right? So we write it as it is. Now what this function is doing, it is simply doing a constant work, and it is making a call to itself by reducing n by 1. So in recurrence tree also we are doing the same thing. This function is doing a constant amount of work, and then it is making a call to itself by reducing n by 1. Clear? As it is a recursive function, so f of n-1 is again going to make a recursive call, and along with it, it does the constant work. So we draw like this. It does the constant work, and again it makes a recursive call to itself by reducing n by 1. Now n become n-2, because n-1 is going to be n-2. Now f of n-2 is again going to do some constant work and make a recursive call of n-2 minus 1. So it becomes n-3, and this process continues. Now let's calculate the amount of work we are doing at each level. So if you look at this program, at each recursive call we are doing the constant amount of work. So at this level we are doing constant amount of work, at this level also we are doing constant amount of work, at this level also we are doing constant amount of work. So the amount of work done on each level is going to be a constant, right? Now the question is, how many levels we are going to have for this recursive call? We have started from n, then we go to n-1, then we go to n-2, then we go to n-3, and this process continues. So we assume that this process continues till n-k. So we are going to have k levels in this recursive tree. So the total levels is going to be k. Now we don't know the value of k right now. We will find the value of k soon. Okay. Now understand this. If we call this function, and this function calls recursively every time by reducing the n by 1, we reach at a level where n becomes n-k, right? And this, if you see it, if you look at this carefully, this is our stopping condition. Let me show you in the code. See, this is our stopping condition when n becomes 0. So obviously when we reduce n by 1 every time, there is a point in time when n becomes 0. So this is going to be our stopping point. At this stopping point, our value of n is going to be 0. See, we have reached here, right? So we can write that n minus k at this point, our n minus k is equal to 0. So we can write that the value of n is going to be 0. At this point, we are returning control back to its parent, right? So by solving this, we get our k equal to n. So now we know that how many levels we have. We have n levels total. Now let's calculate the total work done in this recursive function. So it's going to be the amount of work we are doing at each level and into the number of levels, right? So it comes out to be c into n. And c is a constant, and in asymptotic analysis we do not care about the constant. So in terms of asymptotic notations, we can write that the amount of work done in this recursive function is going to be theta of n. And this is the exact bound. Clear? So far, so good. And this is how we construct recurrence tree and solve it to find the order of growth of this recursive function. Great. Now let's move on to our next example. Now let's see this example. In this example, we are doing constant amount of work, and then this function is making a recursive call to itself by reducing the input by 1. So the recurrence relation of this function is Tn is equal to Tn-1 plus Tn-1 plus c. Now let's try to construct the recurrence tree of this recursive function. So for the sake of simplicity, I am using only n. I have removed the f. to save some space. Okay. Now when we call this function, it means our input is n, and what we are doing, we are simply doing a constant operation and making a recursive call 2 times by reducing the n by 1. So this function is going to make 2 calls, 2 recursive calls for n minus 1 and n minus 1. Now n minus 1 is again going to do some constant work and make a recursive call to n minus 1 minus 1. So it becomes n minus 2, and this process continues. So the input is going to reduce at each level of the tree. Now let's calculate the amount of work we are doing at each level. So here we are doing constant amount of work. So when we call the function first time, this function does constant amount of work, and we can write this as a 2 to the power 0 into c. 2 to the power 0 is nothing but 1, so 1 into c becomes 1 only. Now this function is making 2 recursive calls. So the amount of work we are doing here at this level is 2c, because this function is doing constant work here, and it also going to do constant work here. So c into c becomes 2c. So similarly at this level also, this function is going to do 2 to the power 2c amount of work, and so on and so forth. Now this process continues till n minus k. How? See, in each level we are reducing n by 1. So we assume that this process continues till n minus k, right? So the amount of work done at the last level is going to be 2k into c. Alright, so now the amount of work done at each level is going to be what? Let's see it. So first of all, c is the constant, so we can substitute the value of constant with 1. So it comes out to be the amount of work done at each level is going to be 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2 plus 2 to the power 4 till 2 to the power k. So this is the total amount of work done at each level. Okay. Now after solving this, we get 1 plus 2 plus 4 plus 8 plus ... 2 to the power k. Now if you observe this series carefully, you can see that this is nothing but a geometric progression, okay, with a common ratio of 2. And the geometric progression looks like this: a plus ar square plus ar 4 till ark. So here our a is 1 and r is a 2. R is a common ratio. It means if you take any 2 term in this series, let's say we are taking 4 and 2, and you divide the second term by 1 term, so you get the common ratio. So we get 2 as a common ratio. Now if we multiply this common ratio with any term, you get the second term or the upcoming term. So for example, if we multiply 2 by 1, we get 2. If we multiply 2 with 2, we get 4. If we multiply 2 with 2, we get 8. So this is how geometric progression looks like. So now the formula to find the sum of this series is going to be a into r to the power n minus 1 divided by r minus 1. So let's substitute the value of a and r. So after substituting the value of a and r, we get 2 to the power k minus 1 divided by 2 minus 1. It turns out to be 2 to the power k. Now the only question is we have to find the value of k. It means how many levels this tree is going to be. Okay. Now as same as the previous example, we have reached till this level, and this is the stopping point of this recursion calls, right? So at this level our value of n becomes what? 0. So n minus k becomes 0 at this level and our recursion stop. So we can write that n minus k is equal to 0, and we get the value of k as n. So it means the number of levels in this recursion tree is going to be n. Now let's substitute the value of k to this sum. After substituting value of k to this term, we get 2 to the power n. And in terms of asymptotic notation, we can write the time complexity or the order of growth of this recursive function is going to be theta of 2 to the power n. Great. Now let's move on to our next example. So in this example, our function is simply doing some constant amount of work, and this function is making a recursive call to itself by dividing the n by 2. And the recurrence relation of this function is Tn equal to Tn divided by 2 plus c. Good. Now let's construct the recurrence tree of this function. Okay. So at first we are calling this function by passing n to it. So we can write it like n divided by 2 to the power 0. Why we are writing this like this? Because we want to guess the pattern. Okay, that's fine. Obviously 2 to the power 0 is 1 and n divided by 1 is n only. Okay, so when we call this function does some constant work and make a recursive call to itself by dividing n by 2. So we are doing the same thing. When we call this function does some constant work and then it calls itself by dividing n by 2. So now this time 2 becomes 2 to the power 1. And again this function makes a recursive call to itself and it becomes n divided by 2 to the power 2. And this continues up until n divided by 2 to the power k, right? Because at some point this 0, 1, 2, 4 becomes k. So we are assuming that this recursion tree is going to have a k levels. And at each level we are doing constant amount of time. So the amount of work done at each level is going to be constant. And how many levels we have? We have k levels. Now let's find the value of k. So this is the point where our recursion is going to stop. And at this point the value of n is going to be 1. So we can write that the n divided by 2 to the power k is equal to 1. So when we solve it, we get n equal to 2 to the power k. And when we take log both the side, we get the value of k is log base 2 of n. Now let's calculate the total amount of work done. So the total amount of work done is equal to work done at each level into number of levels. So the amount of work done at each level is c and the number of levels are log base 2n, right? So the time complexity or the order of growth of this recursive function is log base 2n. We are just ignoring constant because in asymptotic analysis we generally do not care about 1 plus 1 minus or any constants. Clear? Now let's move on to next example. This function is also doing a constant amount of work and this function is making two recursive calls by dividing n by 2. The recurrence relation of this function is Tn is equal to Tn by 2 plus Tn by 2 plus c. Alright, now let's construct the recurrence tree of this recursive function. So at first call we are passing n to this function, so it becomes n divided by 2 to the power 0. Obviously 2 to the power 0 is 1, so it remains n. Okay, now this function is going to make two recursive call by dividing n by 2. So now our n becomes n by 2 to the power 1 and n by 2 to the power 1. Now this recursive call at this level again going to make two recursive call. Now the value of n becomes n divided by 2 to the power 2 and so on and so forth. And this process continues till we reach n divided by 2 to the power k. Now let's calculate the amount of work we are doing in this function at each level. At each level we are doing the work. How much work? The constant work. Okay. So we are doing constant work here. We can write it as a 2 to the power 0 into c at each level. Now at this level we are doing 2 to the power 1 constant work because we are doing constant work at this call and constant work at this call. So it becomes 2c. At this level we are doing 4c. So we can write 4 as 2 to the power 2. And at this level we are doing 8 constant work. So we can write it 2 to the power 4. And this process continues, and at the last level we hopefully doing the 2 to the power kc constant work. Okay, now the amount of work done at each level is going to be same as the previous example. We have seen that this is simply a geometric progression. At this time the sum is going to be 2 to the power k. Now here let's find the value of k. Okay, at some point the value of n divided by 2 to the power k is going to be 1. Because why 1? Because we are dividing the n by 2 and the smallest value we get when we divide a number by 2 is 1, obviously, right? So that's why the value of n divided by 2k is going to be 1, and when we solve this we get k is equal to log, and when we solve this we get the value of k as log base 2 of n. So when we substitute the value of k to this sum, we get 2 to the power log base 2 of n. So we have the log of base 2 and this is also a 2, so cancel out each other and we can write it as a n. So the order of growth of this recursive function is going to be theta of n. Let's move to next example. In this example, now we are not doing any constant work. We are simply doing linear work here because we are running a loop from 0 to n, and whatever the value of n will be, our loop is going to run from 0 to n. Okay, the recurrence relation of this function is Tn is equal to Tn divided by 2 plus Tn divided by 2 plus c. Why? Because this function is making a call, to recursive call to itself by dividing n by 2. Now let's construct the recurrence tree of this recursive call. So when we first time call this function, our input is n. We can write n divided by 2 to the power 0. And this function does some linear amount of work, right? See, this function is doing some linear amount of work here and then making a 2 recursive call. Now at this level also, this function is doing linear amount of work. Now why linear? Because we are dividing n by 2. So if we divide 5 by 2, it becomes 2.5 and 2.5. And we sum and we add 2.5 plus 2.5, it becomes again 5. So that's why at this level also we are doing linear amount of work. Now at next level also we are doing linear amount of work. And here this function is making a recursive call to n divided by 2 to the power 2, means n divided by 4. So this process continues, and at some point we reach that our n becomes n divided by 2 to the power k. And this is our stopping point, means this is going to be our base condition in recursion. And our base condition says that when n becomes 1, return. So our recursion is going to stop at this point. So now let's see how much amount of work we are doing at each level. At each level we are doing linear work. In second level also we are doing linear work. In third level also we are doing linear work. And at the last level also we are expecting to do linear work only. So the amount of work done at each level is equal to n. And how many levels we have? We have k levels. Now let's find the value of k. So this is the point where our recursive call is going to complete. So n, the value of n at this point is going to be 1. So n divided by 2 to the power k is equal to 1. After solving this, we get the value of k is log base 2 of n. So the total amount of work done in this recursive function is going to be amount of work done at each level, that is n, into the number of levels we have. So it turns out to be theta of n log n. Alright, so far we have done a great progress. So let's move on to our next example. Now this example is a little bit tricky because in this example this function is making a recursive call, but look at this carefully. This function is making a recursive call to n-1 and it is making a recursive call to n-2, and these both are different values, right? So both the functions are growing with a different speed. The recurrence relation of this function is Tn is equal to Tn-1 plus Tn-2 plus c. So let's try to construct recurrence tree of this recursive function. So when we try to construct recursive tree of this function, so first we call this function with input as n, and this function makes two recursive call, one for n-1 and one for n-2, along with some constant operation, right? Now this recursive function again makes two call. Now this recursive function again makes two call to n-1 and n-2. So it becomes n-1 minus 1 n-2, and n-1 minus 2 becomes n-3. And this recursive function again going to make two calls to n-1 and n-2. So n-2 minus 1 becomes n-3, and n-2 minus 2 becomes n-4, and this process continues. And at each level we are doing this amount of work. At first level we are doing constant amount of work. At second level we are doing 2c amount of work. At third level we are doing 4c amount of work. And in fifth level and in fourth level we are doing 2 to the power 4c amount of work. Now if you observe this tree carefully, you can see that the left part of the tree is growing very slowly. It means at each level we are reducing n by only 1. Let's See, here it is n, here it is n minus 1, here it is n minus 2, here it is n minus 3. And on the right side of the tree, we are reducing n by 2. See, the first it is n, then it becomes n minus 2, then it becomes n minus 4, and then it becomes n minus 6. So we have seen in the previous example that all the leaves of the trees are at the same level. But now the thing is different. The left side of tree is growing very slowly, and on the other hand the right side of tree is growing very fast. So if we observe this very carefully, you can see that the right side of the recursive call is going to complete very early as compared to the left side. The left side of the recursive call is not going to complete so early. It takes time. So it's going to complete very late. So in those scenarios, we cannot say the exact bound of our recursive function because we don't know when our recursive function gets stopped. So in those cases, we are going to take the help of our best friend, that is big O notation. So in this type of scenarios, we can say that we don't know the exact bound, but we can give the upper bound of this recursive function, and it is okay. Anyway, we want to know the worst case scenario or the worst case order of growth of any algorithm or recursive function, right? So in this example, we are using the upper bound only. As we do not know the exact bound, we can find the upper bound of this function anyway. So at each level, we are doing some work, and that is again a geometric progression. See, at first level, we are doing C amount of work. At second level, we are doing 2C amount of work. At third level, we are doing 4C amount of work, and so on and so forth. So it is again a GP. So after solving this GP, we get the amount of work done at each level is going to be 2K. Now, how to find the value of K? So if we look at our example, we see that when the value of n becomes 0, we are just returning. And what is the last leaf of this tree? See, we are reducing n by 1. Last leaf of this tree is going to be n minus k, right? So we can write n minus k is equal to 0, and we get the value of k as n. And after substituting the value of k to this expression, we get 2 to the power n. So as we talk about the upper bound of this recursive function, we can say that the upper bound of this function is going to be big O of 2 to the power n. So I hope now you have good understanding about how to write a recurrence relation, how to construct recurrence tree, and then how to calculate the order of growth of a recursive function. So this is it for this video. Thanks for watching. See you in the next video.